Hey guys, let's do a gravitational fields problem. Newtonian Gravitation 1. A satellite of mass 228 kilograms is located 8.26 times 10 to the 6 meters above Earth's surface. A. Determine the magnitude and direction of the gravitational force. And B. Determine the magnitude and direction of the resulting acceleration on the satellite. So I'm going to start off this problem by drawing a picture to get a sense of what's going on. Okay, so draw your Earth. And then nearby, draw something that appears like a satellite. Now, based on this picture, I'm going to start labeling what I'm given in this problem. For example, I'm told the mass of the satellite, so I'm going to label that m sub s. So m sub s is 228 kilograms. I'm also told the distance that the satellite is above the surface of the Earth. So that's this distance right here. So I can call that rs. Okay? Equals 8.26 times 10 to the 6 meters. Now there are two other pieces of information in this problem that we weren't explicitly given, but are features that you could always look up either in a table or on a formula sheet. And that is the radius of the Earth, okay, so the distance from the center to the surface, the radius of the Earth, so let's do that over here. If you don't already have this memorized, you will by the sheer number of problems that you'll probably have to do. 6.38 times 10 to the 6 meters. And we also know the mass of the Earth. Mass of the Earth is 5.98 times 10 to the 24 kilograms. Okay, so now we've got a lot of information. And all we're asked to do really is find the magnitude and direction of the gravitational force. Now, usually when we're on Earth, we can just use the formula Fg is equal to mg, right? M is the mass of the object, g is the acceleration due to gravity on Earth, 9.8. Now, in this question, because the object is not on the surface of the Earth, it's quite a ways away, we're going to use this formula. Fg is equal to g ms me divided by the total distance rt squared. Now, the reason we have to use this is this accounts for a different value of g. The value of g is 9.8 at the surface, but as you go far away, and this is quite a ways far away, okay, this is even further than another radius of the Earth, this value of the acceleration is going to decrease, so you can't use this formula anymore. If you're ever unsure, this formula always is going to be accurate. So, our capital G, the universal gravitational constant, is it's a constant. So it's 6.67 times 10 to the minus 11 Newton meters squared per kilogram squared. The mass of the satellite is 228 kilograms. Mass of the Earth, 5.98 times 10 to the 24 kilograms. And we're dividing that by the total distance squared. Now, this is exactly why I drew the picture the way I did. I've got radius of the Earth, radius between the distance between the surface of the Earth and the satellite. This r in the denominator of the universal gravitational formula is the distance between the centers of the mass listed here and the mass listed here. In other words, it's this distance right here. But if you look at that distance, RT, it's simply RE plus RS. Okay, so this is just RE plus RS. So 6.38 times 10 to the 6 meters plus 8.26 times 10 to the 6 meters. Don't forget to square that. Okay, so this is a big calculation, so I'm going to do it in two parts. Numerator first, then denominator. Okay, when you solve for the numerator, you can see that you've got 2 kilograms multiplying and a kilogram squared in the denominator. Those are going to cancel. And we get in the numerator 9.0941 times 10 to the 16 Newton meters squared. In the denominator, before squaring, you're going to get 1.464 times 10 to the 7 meters. Okay, so you can see you're going to have a meters squared in the bottom and meters squared in the numerator. You're left with newtons, hence the unit for force. Okay, when you plug all those in, you're going to get a force of gravity of 424 newtons. Now, the question says determine the magnitude and the direction. So because I want to put a direction now, I'm going to put a little vector symbol on top of my force of gravity, and I'm going to state my direction in square brackets. The direction for gravity, because gravity is an attractive force. Unlike the electromagnetic force, it only attracts, it cannot repel. So the attractive force for the satellite is towards the center of the Earth. So towards Earth's center. Okay, so that's the answer for part A. Okay, so B, determine the magnitude and direction of the resulting acceleration of the satellite. So remember in the beginning I said we can't use this formula because the value of g of 9.8 meter per second squared is only valid on the surface of the Earth, which is why we had to use this formula in the first place. Now, if you compare the two of them, you've got mg and you've got gmm over rt squared. Okay, the only real difference here is here, here, and here. Those three elements are different, right? So if you actually compare the two formulas, you can actually gather that for part B, your acceleration due to gravity is simply g me over r squared. Okay, so what's the mass causing the acceleration due to gravity? That's the g. That's the mass of the Earth. G is your universal gravitational constant. R is the distance between the center of that object, the Earth, and where you are. Okay, so if we plug those values in, so you get 6.67 times 10 to the minus 11 Newton meters squared per kilogram squared times mass of the Earth, 5.98 times 10 to the 24 kilograms, divided by the distance squared. Okay, so the distance would be that RT value, the 1.464 times 10 to the 7. 1.464 times 10 to the 7 meters, and that's getting squared. Okay, so just be careful with your units there. When you crunch those numbers, you are going to get 1.86 meters per second squared. And the direction, again, it's going to be towards Earth's center. So there you have it. Now, because we're putting a direction, you have to put the vector symbol on top of the g. Now, if you wanted to solve this using Newton's second law, you can do the same thing. So I'm just going to briefly show you how to do that as well. Okay, so if you just take a look at the satellite, ask yourself, what would the free body diagram for that look like? You know, ignoring air resistance. You would have force of gravity going down, and that's about it, right? That's what the force that's keeping it going in that circular motion around the Earth. So you could say that F net is equal to Fg here. And what is F net? F net is ma. What is Fg? Well, we just found it. It's 424 newtons, right? So what's the mass here? In the case of Newton's second law, this turns out to be the mass of the satellite. So acceleration is 424 newtons divided by 228 kilograms. And when you do that, you're also going to get 1.86 meter per second squared, of course, towards Earth's center. So I just wanted to do that to illustrate a point that in physics there are multiple ways to arrive at the same answer as long as your logic is correct. So that's it for the video, guys. Be sure to smash that like button if you liked it and subscribe to Physics in the Flesh to keep seeing new videos from me, which I post every weekday at 12 noon. I can't wait to see you guys tomorrow at 12 noon for video 144, Newtonian Gravitation 2. Alright guys, that's it for this video. I hope you enjoyed it. If you did, be sure to smash that like button so I know what I'm doing makes sense to you guys. And you know how you can stay tuned for my latest videos? By subscribing to Physics in the Flesh. I post every weekday at 12 noon, and this way you guys can always be the first to know when I post a new video. As always, guys, thank you so much for watching. If you missed any of my earlier videos, be sure to click over there on the right. You can click and watch those videos on your screen right now. Anyways, guys, Physics in the Flesh out. Woo-hoo! Holy, my nose looks big on camera.